Hey, Ben, come on in. So, I was looking over your latest schematics. Before we get into the nitty-gritty of your design, I figured we should take a step back and just really lock down the fundamentals. How we get from this abstract Boolean logic on a screen to an actual physical circuit that works. It's everything, right? So what's on your mind? What's the biggest hurdle for you right now?
Honestly, that's exactly it. My main hangup is right there. I can handle the Boolean algebra, no problem, but translating that into physical components, that's where I feel like I'm missing a step. How does a simple line of code, a function, actually turn into a real circuit with switches that do something?
That's the perfect question, and closing that gap is exactly what we're going to do today. I've laid out a little roadmap for us. First, we'll go over my design blueprint. Then we'll talk about the two basic ways to connect things, series and parallel. After that, we'll dive right into a more complex design. And then, and this is super important, we'll get into the art of verification. Finally, we'll cover the mistakes I see all the time, and then wrap up with one more example just to make sure it all sticks. Sound good?
Yeah, absolutely. Let's do it.
All right, let's jump in. Look, the secret to not making mistakes isn't being smarter than everyone else. It's just having a really solid process. I call this my design blueprint. If you follow these steps in this order every single time, you'll catch almost any mistake before it becomes a real problem.
So here it is, just 6 steps. Step 1, and you can't skip this, ever. Find both your main function, f, and its complement, f prime. Second, you just map the logic. And operators become series connections, or operators become parallel. Easy enough. Third, you pick the right switch for each input. We'll get to that in a sec. Then you actually build the two parts of your circuit. The pull-up network, that's your main function, f. It connects your output to the power source, literally pulling the voltage up to a 1. Then you build the pull-down network using f prime, which connects the output to ground, pulling the voltage down to a 0. This way, your output is never left floating in some weird, undefined state. And the last step? Verify. You always verify.
Okay, so that third step, choosing the switch, is super simple but so important. If you have a normal input, like X, you grab a normally open switch. It's off by default and only closes the circuit when X is true. But if you have a complemented input, like X prime, you have to use a normally closed switch. It's on by default and only opens up, breaking the circuit when X is true. You see, it's the physical version of a NOT game.
So quick pop quiz, Ben. Based on what we just said, if you're looking at your function and you see a z prime, what kind of switch do you automatically know you need?
That would have to be a normally closed switch, right? Because it's on by default until z goes high.
Exactly. You've got it. Simple as that. Okay, let's keep moving.
All right, next up are the two fundamental ways you can connect these switches. Think of this as the basic grammar for our circuits. Literally every complex thing you'll ever design is just some combination of these two patterns.
It really just boils down to this. When your logic says AND, you build in series. It's like a one-way street with two gates. For the electricity to get through, switch X and switch Y have to be closed, both of them. Now, when your logic says OR, you build in parallel. This gives the electricity choices, different paths it can take. It can go through switch X or it can go through switch Y. As long as one is open, you're good. Just burn this into your brain. AND is series, OR is parallel.
Okay, that makes sense. The checklist, the switch types, series for AND, parallel for OR, I think I'm ready to actually try it.
Good. That's what I want to hear. Let's put this theory into practice with a real design challenge. Okay, here it is. This is the function I want you to build a circuit for. F equals z prime and the quantity y or x. See? It's got a little bit of everything we've talked about. A complemented input, an and an or.
All right, Ben, stop. Don't even think about drawing anything. Look back at our blueprint. What is step 1? The absolute, non-negotiable first thing you have to do.
Right. Step 1 is find the complement. So f prime, using De Morgan's laws, that would be z or the quantity y prime and x prime.
Perfect. See? You haven't drawn a single wire, but you already know the logic for both halves of the circuit. This is how you stay out of trouble and build things that work predictably.
And this is what it looks like when it's all put together. Let's walk through it. The top half, our pull-up network, is our function f. We've got a normally closed switch for z prime, and that's in series with a parallel block for y and x. Makes sense, right? Z prime and y or x. Now, the bottom half, the pull-down, is f prime. Here we have a normally open z switch in parallel with the series block of normally closed switches for y prime and x prime. Z or y prime and x prime. See how they're complements? The output VO is always firmly connected to either power or ground. It can't float.
Okay, so the circuit looks right. On paper, it seems to match our logic perfectly. But here's the thing about engineering. Looks good doesn't cut it. You have to prove it. Designing the circuit is only half the battle. Verification is the other half, and you could argue it's even more important.
I get it. So even though I followed the checklist and the schematic looks like it should work, I still have to prove it formally. So how do we do that? How do we know for sure, 100% sure, that this physical thing will behave exactly like that abstract function we started with?
Excellent question. Well, the first way is just brute force. We build a truth table. We test every single possible combination of inputs. Since we have 3 inputs, x, y, and z, that's 2 to the power of 3, which is 8 possible combinations. Let's just pick one. Say x equals 0, y equals 1, z equals 0. We plug that into our original function, f equals z prime times y plus x. That becomes 1 prime times 1 plus 0. So that's 1 and 1, which is 1. The output should be high. And if we look at our table for 0, 1, 0, yep, VO is 1. You just have to do that for all 8 rows.
Now, the truth table is fine, it works, but it can be a bit of a slog. A much more elegant way to do this is with a Carnot map, or K-map. What we do is take all the 1 outputs from our truth table and plot them here. Then, the magic happens. We draw boxes around adjacent ones, in groups of 2, 4, or 8. Here, we can draw 2 overlapping boxes. This green group simplifies down to just z prime y. The orange one simplifies to z prime x. Put them together, you get z prime y plus z prime x. Factor out the z prime, and what do you have? Z prime times y plus x. It's a visual proof that our circuit does exactly what we want it to do. It's fast and incredibly powerful.
Wow, okay, the K-map is pretty slick. A visual proof? I like that. I feel like I have a really solid process now. So, what are the common mistakes? What are the things that usually trip up new engineers?
I am so glad you asked that. Let's talk about the rookie mistakes. I'm going to walk you through the 4 errors I see junior engineers make all the time.
Okay, number 1, and this is the big one. They forget the F-prime network entirely. They just build the pull-up. The problem is when the function is false, the output isn't connected to anything. It's just floating, and that leads to totally unpredictable behavior. It's a catastrophic error. Number 2 is just mixing up series and parallel. It's an easy slip-up, so just double-check yourself every time. And as series or as parallel. Third, using the wrong switch, like grabbing a normally open one for z prime. And finally, number 4 is messing up right at the beginning, getting the complement calculation wrong. If your F prime is wrong, the whole bottom half of your circuit is guaranteed to fail.
You know, talking about it is one thing, but doing it is what makes it stick. Let's do one more super quick example, just to really hammer this design and verify workflow into our heads.
Okay, Ben, you drive this time. The function is as simple as it gets. F equals A or B or C. What are the first 2 things you do?
Okay.
First, find the complement. F prime is A prime and B prime and C prime. Then I map the logic. For the main function F, all those ORs mean I need 3 switches in parallel. For the complement F prime, all the ANDs mean I need 3 switches in series.
You nailed it. And this is what that circuit looks like. It's the perfect physical version of that logic. The pull-up network is F, 3 normally open switches in parallel. The pull-down is F prime, 3 normally closed switches in series. It's clean, it's simple, it's correct.
And for the final step, we verify. Let's skip the truth table and go straight to the K-map. We plot our ones, and look at that. We get 3 big overlapping groups that simplify right back to A plus B plus C. The design is 100% confirmed. The process just works. So I want to leave you with this one thought, Ben. A great engineer isn't someone who designs things perfectly the first time. Nobody does that. A great engineer is someone who has a process that is so solid, it finds every single mistake before that design sees the light of day. And your number 1 tool for that is verification. Never skip it. Ever. So, does this all feel a bit clearer now?
Crystal clear. Blueprint, build, verify. I got it. Thanks, Alex. This was a huge help.